All right, class, we're gonna get started. Okay, so just to know, so we have today we're gonna cover lectures 17 and 18. We're gonna start with 18 rather, because the continues on ANOVA, and we're gonna talk about three factors of ANOVA in lecture 18. So we'll start from 18, then we'll move to 17. Another note, I have not finished grading your quizzes, so we're not going to spend the end of this class period talking about your quizzes. I want to make sure I know what are the kind of common mistakes that I've seen on each problem before we go through them. So that'll have to be on this coming Monday. Any other questions or anything before we get started? Yeah. This Monday is not a quiz. When is the next quiz? The following Monday. So a week from Monday is a quiz. Yeah, exactly. Right. All right. Any other questions? Okay, so there were two questions that I just want to follow up on from last time in class. The first was about that C that we put in. So we factored when we were setting up our problems using statsmodels.ols for analysis by ANOVA, and we were doing two-factor ANOVA. We formatted our model as output is a function of C of input 1 plus C of input 2. So that the question was, what is that C there for? What does it do? So that C there is telling the statsmodel.ols routine that these are categorical variables. And that's actually one of the assumptions going into the ANOVA, our overall procedure for ANOVA, is that we're doing this on categorical variables. So even if we have, so for example, when we were looking at the tomato yield example, we had different types of tomato seed was one of our factors. So that's definitely categorical, right? We coded it as numbers, but then we have to use this C tag in order to tell OLS that it should treat that, even though we're giving it numbers, we should treat those numbers as categorical variables. And then for we also have the density, which is quantitative, but in this case we had just chosen some discrete levels of the crop density that we used to run our experiments. ANOVA to get our OLS to actually run an analysis that then feeds into ANOVA as we formulated it so far in this class. We need to treat that variable as categorical as well. And so this C of input 1 and input 2 is telling statsmodels.ols to treat those variables as categorical, which is required for it to do ANOVA in the way that we've discussed in this class. So one way to think of it is that we formulate our model this way so that we have met the requirements for ANOVA. So we're actually doing an analysis using ANOVA. You'll notice we also used OLS in actually using OLS, for example, in this homework 10. So we can use OLS for just in regression in general. One way to think of it is that ANOVA is a specific case of linear regression where the input variables are categorical. And that's why we have to specify the variables are categorical in OLS in order to basically be doing ANOVA. But OLS is a more general routine that can do linear regression in general. And so you could just think of this as like I don't know, almost like a magic incantation you have to do to get OLS to set the problem up correctly for the ANOVA downstream. But just a little bit more of the insight into it is that we can only do ANOVA on categorical variables. Any follow-up on that? Hope that's clear. It's getting into kind of nitty-gritty of how some of these routines work. Okay. So then the other question that I want to follow up on from last time was about the formula for the effects of our different factors on the output when we had a two-factor ANOVA. We gave them as, for example, the mean effect or the estimator of the effect of parameter factor A was given as this formula here, and we had the same formula for our beta parameters, for our beta effects, and these are correct for if we have more than one replicate per condition. So it's the same expressions if we have more than one replicate. The difference, which we didn't go into and would be, I guess, beyond the scope of this class, is that if we do have more than one replicate per condition, then we saw that we could also use ANOVA. This part's within the scope of the class. We can also use, if we have KIJ greater than 1, we can also use ANOVA to look at the interactions between the different factors. But I guess what's beyond the scope of the class is that we can then also define similar expressions for what the impact of those interactions are. And there, it's given in your textbook if you're interested in the board textbook. But so there'd be an additional set of expressions for KIJ greater than 1. All right. Any other questions or follow up from last time? Okay, so we're going to, so as I said, we're going to start with 3-factor ANOVA, and then we'll move on to confidence intervals and hypothesis testing regarding variances. So 2 relatively short topics crammed into this one class period. So we're going to start with 3-factor ANOVA. So just as it's sometimes the case that we have more than, that we have 2 factors to consider, and the impact of, we want to know the impact of 2 factors on a particular output. We may have 3 or more factors, and we can do that. We can set up a problem in a very similar way to do 3 or more factor ANOVA type analysis. And so we're just going to walk through some examples of 3-factor ANOVA in this class. We're using the same set. We're using OLS again and the same ANOVA package in Python. So in this case, we're looking at an investigation of compressive strength of cement soil mixtures at 2 different aging periods, 2 different temperatures, and 2 different soil types. Right, so we now have 3 factors. We're given, right, this is the output, this is the strength that was measured as a function of those different inputs for those different input conditions. And we'd like to know what is it that really impacts the compressive strength properties of cement soil mixtures, right, from this set of experiments. Again, this data is stored in an Excel file. We're going to read it with pandas. And now when we look at our interaction plots, right, we now have this like multi-dimensional, right, we have a higher dimension data set. And so we end up with, a higher dimensional data set to look at. Here we're plotting. So instead of just getting a single plot for this interaction plot, we now have 2, 1 in this case for each of the temperatures, where at each individual temperature it's plotted for the individual soil conditions in different colors. So for example, from this, we can see that we would not expect there to be much interaction between the factors, right? Because these lines are mostly parallel to one another. They do, I guess, cross over in this case, but they're still mostly parallel to one another. So we expect that there's not much of an interaction. If we wanted to, we could change the axes of these interaction plots and, for example, put temperature on the x-axis to look for evidence of other types of interactions by changing, for example, what's x and y and so on in our options. But anyway, so what we would conclude from this initially is that so in addition to there not appearing to be much interaction here, at least from what we can see in these plots, it also looks like longer aging time is going to increase strength. So we would expect to see an impact of aging time and increased strength. Yep. Yeah, so is ANOVA only for binomial distributions like yes or no's? No. In ANOVA is, we can think of it as based on a special case of linear regression for categorical variables. right? So commonly in an experiment, we might set up, we can think of setting up that experiment either in terms of qualitative input, right? So it might be like in the previous example, it was tomato type, right? Or we set up the experiment at defined levels of a given input, right? So we say it's going to be, we run this on day 1, day 2, or day 3 or something. So that in ANOVA, when we're running ANOVA, we define those as the categories of those variables that we are using as our inputs, and then we measure some output. And for ANOVA, actually, that output has to be continuously valued output, right? So in this case, like the yield strength can take any value on the output, so it's a continuous value output. But it does not require that there's binomial inputs, like a 1 or 0 on input. So for example, we can have 3 tomato varieties that we're looking at, right? We could have 4, we could have 5, we could have many different numbers of levels. And it's not fundamentally based on distribution. Yeah. Okay. Other questions for him? Sorry, is that a question on the notes in class, or is there something I can clarify? Okay. Thanks. So all right, so from this interaction plot, we can already get some sense of conclusions here, but we want to investigate those a little bit further. So we'll set up our model using this formula. And so now note that when we're considering this 3-factor ANOVA, we now have many more terms in the model. Note that all of these again are set off by this C for categorical, right? So we're taking those variables and telling OLS that even though, for example, age is in there as a number, we want to treat it as categorical because we're going to be doing ANOVA on it. And we're considering, we now have age, temperature, and soil type, but then we also are looking at the interactions among those variables, as well as any potential interactions among all 3 variables. So in this case, we have replicates, so we're able to parse out all of the possible interactions among these variables. And if I scroll up here, you can see we have one indication that we have replicates. We could look at the original data, and that would show that we have replicates. But another indication that we have replicates is we have error bars on these points, indicating that at any given condition we had more than one measurement. And therefore, we're showing not just a single point there, but we're showing the error bars on those points. So indicating that we have replicates. So because we have replicates in 3-factor ANOVA, we can get not only the impact of each of the individual variables, 3 factors, the interactions, the pairwise interactions, and then because we have replicates in 3-factor ANOVA, we can see interactions among all 3 factors together. So when we run this ANOVA, we get the resulting table. This is what we get out, right? So we now have many more rows than we did in 2-factor ANOVA. You can imagine if we go to 4-factor ANOVA, right, it's going to increase still further. Yeah, Max.
Is the slash just saying that that's the next line of the original?
Yeah. The slash just saying continue that string to the next line. That's exactly it. Yep. So that way we didn't have it stretching all the way up too far. Correct.
In the 2-factor, we didn't have this like the CA code system, right? We didn't have that in.
So in 2-factor for multiple replicates, we did. So in 2-factor, let's go back. So in 2-factor, when we're formulating the model for, KIJ equal to 1, we didn't have the interaction term. And we said that's because in 2-factor ANOVA with 1 replicate per condition, we do not have the ability to distinguish any interaction terms. But when we had KIJ greater than 1, then we would want to include this extra term. Okay, does that make sense? Yep. And so one of the big differences in 3-factor is that now we have not only all the single terms, right, all the single factor effects, we have all the pairwise effects, and then we have this like grand total interaction effect. Okay. And what we're going to see in the next example, and this is for Kij greater than 1 in 3-factor ANOVA. We get all of these. In the next example, we'll look at Kij equal to 1, 3-factor ANOVA. And in that case, this is the term. We just don't get this term. So if we get all the rest, we just don't get this term. Okay. So we still get some interaction, some information about interactions, even with Kij equal to 1 in 3-factor ANOVA, but we don't get this big one. Okay, so from this table, so at a significance level of 0.05, are there interactions? So what interactions do you see?
Well, we have an age and temp effect.
Age and temp, but if we look here,
Sorry, you're saying p-values for where the two combinations get there.
so for so from this table, we can see that all of these p-values are greater than, so we're doing this at a significance of 0.05. All of these p-values describing all of these interaction terms are greater than 0.05. So that's telling us that there's no, we don't have any evidence of interactions in this case. And it's also showing us that the soil condition, right, also there's no evidence of that impacting what our final result is. The only significant results would be for age and temperature, right? So we can see there's no significance between at the 0.05 significance levels. And it looks like it's really just those two, age and temperature. So, you know, one thing we can do, so now we have this data set that's higher dimensional. So a lot of what we're going to talk about with 3-factor ANOVA is about trying to kind of reduce that dimensionality so we can see a little bit more about what's going on. So the interaction plot, for example, is one way where we did that, where we plotted just, you know, one axis. We would just do one axis, one set of axes at a time. Yep.
So just about interpreting the results, when you say there's not a significant probability of a combination of age and temperature, is that saying that different ages don't do better under different temperatures? Is that what that's saying, that like this age is better under this temperature, but working for this? Is that what that's saying?
Yeah, so let's look at age and temperature versus the interaction between age and temperature. So what we're saying is that age has some effect, right? This is evidence that age has some effect. And we could use this to estimate what that effect is, right? What the effect of the different levels of aging are on the final output. And separately, temperature has some effect, right? We have evidence that temperature has some effect. We can estimate what that effect is. But what it's saying is that if we then we start from some base case, then we change the age and change the temperature, right? We would expect to see those impacts just be exactly additive. As in, like, the impact of, like, there was some impact from changing the age, and there's some impact from changing the temperature, but there's no additional impact if you change both at the same time. Does that make sense?
Okay, that makes sense.
You know, and that's one of the things that we're looking at in these interaction plots, right? So here we're seeing that we changed the age, right? So this would let us look at the interaction between age and soil. So we changed the age, right? And we saw some increase as we moved from age 1 to age 2. And we saw about the same increase regardless of what the soil content or what the soil condition was. So that's how we can infer that there was no interaction, right? From this plot, we can infer that there's no interaction between, in this case, age and soil. Okay. So this interaction plot is another way. That's why we call it interaction plot. It's another way of inferring that. Yeah. Good question. So we can then look at, we can take this data and slice it and look at the averages for different conditions, basically like holding, it's asking a question of like, if we hold one thing constant, what does the average output look like? And that can give us some insight into what's happening here. If we think back to the expressions we had for those alpha i's and beta j's and two-factor ANOVA, it's actually related to exactly what we're doing when we're trying to figure out what the sensitivity is to each one of these parameters. But for example, we can look at the mean strengths for different combinations of age and temperature. So we can see, for example, if we have age is 1 and temperature is 1, we saw a mean strength of 425 or 426. For age of 1 and temperature of 2, we see an increase in that strength. For age 2, temperature 1, right? So now over our base case, we've increased the age. We see a greater temperature, right? So comparing 425 to 706, we see that age also appeared to increase the overall strength. And then again, combining them, when we combine both age and temperature together, we see this max of 762, right? So it's higher than both. The main thing to take away from this is that it's showing us, like if we just average across all of the conditions where we had age of 1 and temperature of 1, we're looking at what the output is. And this reinforces what we saw in the ANOVA analysis, in that increasing temperature or age over this initial case both result in increased strength. Increasing both together resulted in a further increased strength, but it's in line with there being not much interaction between the two. Yeah.
So sorry to go back a little bit to the when we're back looking at the ANOVA table.
Yeah.
The C age and the C temperature, those are for the interaction on each other, not on the string, right? So the p value there is that discussing if it's the age and temperature having interactions with each other, or that relating back.
It's saying do they have an interaction with each other that impacts strength?
Okay.
So yeah, do they have an interaction with each other that increases strength? So, is it? So it could be that temperature acts differently to improve the strength of the sample, depending upon the age of the sample. Okay, and if so, then we would see an interaction. Then we would see a significant interaction.
Okay. But what we're seeing here is that the age is having something to do with the strength, and the temperature is having to do with the strength, but not necessarily together.
But not necessarily together. Yeah. So so it doesn't look, and that's what we mean by an interaction. Does that make sense? Does that make sense what we mean by interaction here? So it's not that age influences temperature, it's that the combination of age and temperature is different than having those two things adjusted independently. So it'd be like if the older soil behaves differently at higher temperature than the younger soil. Yeah.
I was just gonna ask to clarify, you're basically saying that we see a bigger, less big, whatever, we're seeing a different change than we expect. We just from the age effect and the temperature alone, that's the interaction.
Yeah. Okay. Yeah. Yeah, exactly. Yeah, so it'd be like if you saw a bigger or smaller effect when you had the combined higher age and higher temperature, then you saw a lot of them. Yeah, but I mean, again, understanding what's in this ANOVA table and what information is given to this ANOVA table is kind of the whole analysis for us, at least here. So I'm fine to go back to it as much as we have to. So don't apologize. Don't worry. Okay, so so then from this investigating the means, we would then conclude that both an increased age and increased temperature give the highest strength. Again, just by slicing the data and looking at means at different levels of those parameters. So in example 2, we're basically looking at the same problem, but now without replicates. So now Kij, actually Kijk, I guess, because we have 3 factors. So we have just a single replicate per condition. Kijk is equal to 1. And so what we'll see in this case is that there's not enough data to examine 3-way interactions. So between all 3 of the parameters together, and so we're not going to include them in the model. But otherwise, we're going to get very similar, a very similar kind of analysis. So here, our formula is a little bit different. So we still have all of the individual parameters one by one. Again, we're using that C tag, the categorical tag, because we basically want to be doing ANOVA, not just generalized regression. But in this case, for the case of three-way ANOVA, we are able to, even with one replicate, we are able to look at two-way or pairwise interactions. So we're looking at interactions between agent temperature, agent soil, and temperature in soil. We just can't do the three-way interaction from here. And so when we run this ANOVA, this is our resulting table. And so in addition to noting that we don't have this that bottom row that we had when we had replicates, you can also notice that without replicates, we basically didn't have as much statistical power to detect the impact of these different impacts. And in this case, none of our data would reach even a significance level of 0.05. Right, so none of our effects reach a significance level of even 0.05. Right, so the p-value for age is 0.1. Right, so 0.05 means like 1 error in 20. 0.1 means 1 in 10. And this is typically not considered significant enough. Yeah, just by way of example, we haven't talked about exactly how, in the case of ANOVA, replicates increases statistical power or the ability to distinguish differences. But we can see that having more replicates, in this case, would allow us to draw conclusions that are maybe not possible if we have just a single replicate per image. Yeah.
So the K factor is like a number of the replicates.
Yeah.
Like how many measures at this certain temperature in soil.
Yeah. So Jeff goes in. So in two-factor ANOVA, we said Kij was the number of replicates at condition Ij. And we had two different conditions, one for Kij equal to 1, the other for Kij greater than 1, right? Here we have three factors, so it would be Kijk. And this is the case for Kijk equal to 1, so we only have one replicate per combination of factors.
Okay, and then how do we know if it's greater than 1 or 1? Looking at data.
By looking at the data, the number of replicates, the number of replicates per condition is what we say.
Okay. If there's like, even if there's like one,
yeah. So even if there's one that is greater than 1, then we're in that case, then we're in that greater than 1.
Okay, even if some of them don't have any.
If some of them don't have any, then yeah, we'll consider that later when we start talking about design of experiments and how we do analysis. So yeah, we'll consider that later when we do design of experiments and how we do analysis when we don't have, how we actually choose which levels we're actually going to run experiments for. And we'll look at that analysis.
You kind of going off of that, so you could have two, like, 2 points, so like rotating 2 in one series, but then like not have 2 together.
Yeah, and then we're still technically in Kij or Kijk greater than 1 if we have just 2 replicates of one of the conditions. So we can define, in that case, we can define an interaction term. Right? We can look at a p-value for an interaction term, but we're not going to have very good power to do so. Like we're not going to have very good very good ability to distinguish whether or not that's significant. Because it can only be because we only have that one. We only have that one case where we have the reference. Yeah. So underneath a lot of this is a more advanced concept in statistics. Right. Most of the stuff in this class is focusing on the mechanics of how we do this, and interpret this, and understand what the results are. I guess a lot of the discussion and questions we've gone into the ethics of statistics. How do you choose the right test? And then related to how you choose the right test is the concept of statistical power. I guess for now, I'd say on statistical power, that's like the ability of a statistical test to determine if there's a difference. And things like the number of replicates you have can greatly influence the power you have to determine a difference. Any other questions on that? Okay. So the third example is going to be, so we have delay time of igniter. We're looking at 3 different types of initiators, 2 different types of booster charges, and 4 different types of main charges. Delay time is measured in milliseconds. We want it to be 30 milliseconds or less. 2 replicates are run of the entire factorial design. So we have 2 replicates run of every possible combination of factors, and we're determining which factors significantly affect the delay time. And then for those factors that are significant, we're going to determine which elements significantly affect delay time. So we'll go a little bit beyond our initial ANOVA table analysis. So in this case, this is what our data looks like. This is the start of that data set. Read in again into a pandas data frame. Here we have our interaction plots. And we can see that. So for example, looking at initiator type 1, 2, or 3 on the bottom. And so the delay time is plotted on the y-axis. We can see that these curves are not, in this case, they're not entirely parallel with one another, indicating that there may be some interactions. Right. So we can see that, you know, it looks like there's potentially some interaction here, right, at this between initiator and MC. But we'll use ANOVA to tell us whether or not we can make a conclusion based on that. So in setting this model up, we're again, we're using OLS. Our formula looks like this, where we have, again, all of the individual factors, the pairwise combinations, and because we have replicates, we have the full interaction term. And these are our end results. Note that we, again, if you look at the p-values, right, p-values are over here on the right-hand side for the interaction terms. Looks like even though there was some maybe preliminary evidence for interactions in the interaction plots, we can't, it's not supported statistically, at least in this data set, that there's interaction. And again, it looks like it's just 2 of the 3 factors that appear to have an impact on our final results. So it shows that only the initiator and the main charges are significant or have a significant impact on the delay time. So we find in this case, now we're finding the grand mean. It's just the mean of all the delay time of 19.3 milliseconds. So we can then, looking at these results, just as we did in the previous example, we can group by different, we can look at different groupings, use that to try to understand what the impacts are, right? Because again, we have this multi-dimensional data set. So here we're grouping by initiator and computing the means. So this function here, group by, is going to take our data and group it by that initiator type. And then we're taking that data that was grouped by initiator type and computing the mean. So our end result is a table showing the mean for each of those different initiator types. Right. So we have for initiator type 1, 17, 2, 28, and 3, 13 milliseconds. If we have our data stored in this form, this is just showing how we can access it using a square bracket, just a syntax thing in Python. We could also then do the same thing. Here we're doing the same thing for grouping by main charge, and again, grouping by means. So based on this data, we would then expect that the lowest delay time is with initiator 3, go back up, initiator 3, and main charge 1, right? Because they had the smallest means overall. And we can then estimate that delay time by looking for the mean of all of the data within those with those factors. And so here we're finding the mean of all the data for which the initiator was condition 3 and the main charge is condition 1. We then computing the mean, and we see the lowest delay time of 12.4 milliseconds with that combination. So So again, we slice the data by looking at the means at the different levels, right, in order to try to understand what our results meant for those factors. So provided we don't have interactions, and we showed, remember, that there was no evidence of interactions. Right, our ANOVA table showed that the p-values for all of the interaction terms were greater than 0.05. They're actually pretty large. Then we can use the approach that we'll show here to calculate confidence intervals for the difference of means for two different levels of any one of the effects. Here we have, so for confidence interval on, for the difference between levels 1 and 2 of some factor A, so in this case, this will be, let's say, our initiator. We can find a confidence interval. So it's the difference between those two levels, plus or minus, again, our t statistic. And then the, what we're using for our standard error here is S squared, right? So the standard deviation squared times 2 over B times C times R. So B and C are the levels associated with the factors, B and C, so the other two factors, and R is the number of replicants. And so we can have the same thing for other factors. So for factor B, we're using in the denominator here the number of levels of A and C, and similarly we have the same expression or analogous expression for factor C. Yeah.
The two levels in the confidence interval, if you can compare the two confidence intervals.
Yeah, so this is a pairwise confidence. Right, yeah, so between two levels. Yeah, exactly. So, in this case, we had multiple levels for, so main charges, we had 4 levels, and we can then actually do this. Yeah, good question. Overall, then we can find the, so we find the standard deviation of delay times, the overall standard deviation of the delay times over the entire experiment, over the entire set of experiments as 6.6 milliseconds. And then we're going to basically then use that in our expressions here in order to find confidence intervals on the differences that we observe between any two levels of a particular factor. The degrees of freedom that we're going to use with the t-test. So this is maybe something that wasn't stated up above, but the degrees of freedom for use with the t-test is just that A times B times C. So the number of levels of factor A times the number of levels of factor B times number of levels of factor C times the number of replicants minus 1. And so that gives us our degrees of freedom, and we use that for computing that T alpha. So in this case, degrees of freedom for calculating T was 24, and we get a critical value of 2.06. And then from using that and the expression above, we can then find our margin of error. Right, so very, very analogous to what we've done to find margin of error based on T statistic in other contexts. So from this, then we would look at the differences between means of the delay time. So if we went back up and looked at what the differences in means between the delay times actually were, we see that the differences all exceed this 95% confidence interval on those differences in means. And therefore, we would say that all the 3 means that we saw were significantly different at the 0.05 significance level. Okay, does that make sense? Some sense. We can do the same thing for factor C, the main charge, and we have a margin of error there of 5.6. And if we look at the means of delay times for the first, for the main charges, I'll just scroll up. So this is the differences in means for the main charges. We saw that the differences among these first 3 means here was less than that 5.6. So therefore, we would say that the difference in mean between main charge 1 and main charge 2, for example, is not significant. But the difference in mean between main charge 4 and, for example, main charge 2 is greater than 5.6. And so the difference in mean that we observed between main charge 4 and 2 is significant. So we conclude the first 3 main charges are not significantly different, but the last main charge is different from the others. Okay. All right. Any questions on this? Yeah.
Can you go back to the code for your account calculating the standard deviation? Can you,
Yes.
it's just a little bit down lower, S equals gonna be, right
Mhm.
there.
Mhm.
Can you kind of interpret what that is pulling from? It's taking the mean squares that just made by the AOV table.
Yeah, so it's the mean square. It's one of the parameters that was in the AOV table was the mean square, and this is the mean square for the overall experiment is what we're using, right? So it's mean square. So it's AOV table dot mean square. So the mean square from the AOV table at position overall length of the table -1, which will give us the last value, right, in that table. And so if we look at our AOV table, yeah, that's a good point. So if we look at our AOV table, we're using the mean square, we're using this value here. Right, is what we're pulling out.
Yeah.
Yep. Yeah, sorry, that's actually, that's a great point. So that's telling us if we have this ANOVA table, we have this AOV table, then we need to pull out the confidence intervals on one of the parameters. Then this is the value that we're going to use as the input, as our S,
So we
right?
use S for the whole thing, we never use an S for each.
Yeah, so another underlying assumption for ANOVA we didn't discuss, but that is an assumption, is that in ANOVA we assume that the variances within each grouping are all the same. And so they're like remember when we were talking about one factor in ANOVA, we said that fundamentally what we're doing in ANOVA is trying to see if the difference between means is greater than the difference within means, right? But we often do ANOVA with very limited amount of total data, right? So we don't typically have enough data we often don't have enough data to separately get a really good estimate of the variance within any one grouping. And so what we do instead is pool all the data together to get a better understanding of what the overall variance is. Okay. So and then because of that, when we're looking at the confidence intervals that come out of this, we use just a single standard deviation or single standard error for the entire case.
Okay.
Yeah. Good question. All right. Any other questions on this? Okay. We're going to at least start talking about confidence intervals on variance and standard deviation, which are the lecture notes 17. I think it's likely that we're not going to make it all the way through this because I don't want to be lecturing for more than an hour. I feel like that gets counterproductive. But this is, you can think of it as kind of a complement to what we've been doing most of the time to this point in the class, right? So we've been talking about how we make estimates about about means, right? So oftentimes we have a data set with and we want to answer questions about the means, but there are cases where we might want to where the variance or the variation that we see in the data set, or the standard deviation, the distribution that we see within the data set, that might be the thing that's really important for us to study. So for example, in my lab, we look at cancer cell response to therapy. Right, so we measure the growth rate of cancer cells when they're treated with different therapies that a patient might receive. And then we try to answer questions about whether or not a patient should receive the therapy or shouldn't receive that particular therapy. But a key question is, do all the cells respond in the same way? Because if there's a subset of cells that come from a particular patient's tumor that are resistant to a therapy that we're testing, then we probably don't want to use that therapy because it may lead to resistance to that drug down the line for that patient. And so, for example, in my research, we look at questions of what is the standard deviation, right? Or what is the spread of responses that we see? And then we use that as an indicator of what we would recommend for a given patient. So there can be times when maybe the mean is also important, but you want to answer questions about the standard deviation and or the variance within the data set. And just as we had a set of methods, right, in statistics in order to address questions about the mean, we have a set of methods that we can use to address questions about the standard deviation or the variance within the data set as well. We'll start with confidence intervals, and maybe we'll leave. We have hypothesis testing on variance, and we'll leave that for one day. But we're looking at variance, and we want to compute a confidence interval on the variance. So we have a data set, and we want to know what is the but this is formulated in terms of standard deviation. So we want to know what is a confidence interval on the standard deviation from that data set. This expression, equation 1, is what we can use to develop that confidence interval. So we say that our confidence interval on our estimate of standard deviation is square root of n-1 times our sample standard deviation squared over this chi-squared statistic, and we're going to talk about that for our significance level. And it's between the lower bound and then the upper bound is similar, but with a slightly differently formulated chi-squared statistic. Okay. This expression here comes from the theorem that actually defines what this chi-squared distribution looks like. We're not going to go over that derivation. It's in your textbook if you're really interested, but this comes from the definition of what that chi-squared probability distribution looks like, which we're going to discuss just down below. But one thing to know about the chi-squared distribution is that it has, just like the t distribution, there's just one parameter to define the chi-squared distribution, and it is the degrees of freedom. So let's look at what the chi-squared distribution is. So the chi-squared distribution, this is a plot of the chi-squared distribution as a function of, or for 3 different degrees of freedom. And so we can see for 4, 8, 16, this is what it looks like. And one thing to notice is that it's not symmetric. Right, so almost like the F distribution. Right? The F distribution is not symmetric. The chi-squared distribution is also not symmetric. So when we are looking up values, right, when we were looking up values for the t distribution, we used the fact that it was symmetric to only ever have to consider one of the tails. Right, so on the exam, I gave you a table for the t distribution, and I only gave you one of the tails, information for one of the tails. When we use the t distribution to find a confidence interval or do a hypothesis set, we set it up to only really look at one of the tails. But for the chi-squared distribution, we can't do that, right? So especially as we have lower degrees of freedom, it's very highly asymmetric, and so we are very highly skewed, and so we need to compute the area or the chi-squared statistic separately for each tail. So when we use it, we separately find the critical chi-squared values for both tails of the distribution. So these would be corresponding to areas of alpha over 2 and 1 minus alpha over 2. So we need to find both of those separately. So we have an example here. So this example, we're basically that formula that was up above in equation 1 is put into practice in this code block here to find the variation, or basically find our confidence interval on a standard deviation sigma. It takes as its input some sample data set and the confidence interval. And then you'll notice it's finding degrees of freedom is the length of the sample minus 1, just as we had for the t-test. We're finding the variance and the standard deviation of the data. And then when we find the chi-squared statistic, we actually find it twice, once for one minus alpha over 2, and one's for alpha over 2. So we're finding the chi-squared statistic for both tails, right? Because that was an important distinction here. We can't just use one of the values. And then this is computing the lower and upper limits using the expressions that we had up above, and then we're going to display those results. So this is our data, and this is our confidence interval. When we run that function, we end up with our confidence interval for the population as between 276 and 564. Right. And we can see that this is, fairly broad because we had a highly variable data set. If we look at the data here, it ranges pretty widely from value to value. It's also pretty broad because we had a low number of samples, and so we didn't have much power to distinguish, to nail down what this standard deviation really is. One thing to note is that this chi-square distribution assumes that the underlying data is normally distributed. And so, as is often the case, when we don't have that much data, we're going to say that looks enough like a normal distribution for us to satisfy this assumption. If we had a lot more data, we might have to revisit that. But that shows us the process that we can use the chi-square distribution to calculate a confidence interval on data. So I think we're going to end there for now, just with an introduction to this topic. On Monday, we're going to pick up and we'll talk about the second example. We'll see how far we're going to get into the next lecture notes, and then we will also talk about the quiz on Monday. All right, any other questions before we back up? All right, thank you all.